Hello and welcome to Today I Learned Climate, the podcast where you learn about climate change from real scientists and experts. I'm your host, Laur Hesse Fisher from the MIT Environmental Solutions Initiative. We're continuing our series on energy and climate in partnership with the MIT Energy Initiative. In our last few episodes, we've covered the challenges of adapting our electric grid to take on much more clean energy. But there's another way to generate tons of electricity without pumping greenhouse gases into the atmosphere, a technology that's already mature, widespread, and competitive with fossil fuels, and also very controversial. I'm talking about nuclear power. Today, we'll explore how nuclear power works, why even some climate advocates don't agree on using it, and why many energy experts, including many at MIT, say it's a critical part of our clean energy future. To dig into this, we sat down with an MIT professor who spent his career studying nuclear energy.
I'm Jacopo Buongiorno. I'm a professor in the Department of Nuclear Science and Engineering. I'm also the director of the Center for Advanced Nuclear Energy Systems.
Let's jump right in. What exactly is nuclear power? Well, it all starts with a process called nuclear fission, which is where a nucleus inside of an atom splits, releasing some of the energy that binds the atom together.
This shows up in the form of heat, and then you can convert that heat into electricity that is sent to the grid. And so in that sense, it's a heat source, just like burning coal, natural gas, or getting heat directly from the sun. But the primary energy source in this case is uranium.
Uranium is a heavy metal that's found in rocks all over the world. For this episode, it'll be helpful to know that most of the uranium out there is a kind called uranium-238. And you need to alter or enrich some of that to another type, uranium-235, in order to use it in nuclear power plants. More about that later. The first nuclear power plant was built in 1954 near Moscow. And for the next 30 years, power plants started popping up all around the world. At the time, many people saw nuclear power as a huge leap forward from fossil fuels. For one, uranium is super abundant.
There is an enormous amount of uranium out there, more than enough to continue to use nuclear and grow it, actually, and grow its use for centuries. That essentially affords countries a certain level of energy security. The second feature that makes nuclear attractive is that the energy density of the uranium fuel is many orders of magnitude higher than conventional fuels. And it has to do with the fact that in a nuclear fission reaction breaks nuclear bonds, not chemical bonds, and therefore liberates a lot more energy. So just to give you an idea, a nuclear power plant that would generate enough to power the city of Boston would require of the order of 3 kilograms of uranium-235 fuel per day. And that's something that I can hold, on the palm of my hand. So that tells you how much energy there is in this material.
Today, we see another very important benefit of nuclear power. These power plants don't emit any of the greenhouse gases that are driving climate change.
You have an energy source that essentially does not have any emissions into the atmosphere. And so that's the first reason why people are interested in nuclear now, because, of course, we're trying to minimize the carbon emissions into the atmosphere to prevent massive global warming and climate change.
Nuclear power could have an especially important role to play because it's both clean and dispatchable. That means that, unlike wind and solar, nuclear power can be revved up to produce electricity exactly when we need it. If you want to dig into this topic a little bit more, check out our episode on renewable energy. Today, about 20% of our electricity in the United States is generated using nuclear power. That's more than solar, wind, and hydropower combined.
In the US, over 50%, 50, of our carbon-free electricity today comes from nuclear. So it's already the largest clean energy source that we have on the grid today.
Okay, but hold on. If nuclear power is such a great way to get clean, reliable electricity, and we're already using it, then why aren't we building more? Well, many people, and even entire countries, are nervous about it. There are three main concerns: nuclear waste, nuclear bombs, and accidents. Let's start with waste, which is radioactive and needs to be kept away from people.
In our community, we call it spent fuel. It's basically the material, the uranium, and the products of the fission reaction that come out of the reactor when the reactor is refueled. And it's usually put in water pools, and it cools down for between 5 or 10 years, after which the spent fuel is put in dry casks. So these are steel and concrete little containers, and they are air-cooled.
In the United States, these dry casks are stored at the nuclear power plants themselves. Other countries are building underground storage facilities to store their nuclear waste. Finland is planning to store waste in a bedrock that's been around for about 1 billion years and isn't susceptible to earthquakes. They say their waste will be safe for 100,000 years.
It's one of few industries, I think, in the whole economy that actually takes care of its materials from cradle to grave, right? So nothing is emitted into the atmosphere or in an uncontrolled manner. I don't think any of the other power generation technologies do this.
There's another reason we need to be really careful about uranium, and it's the second big fear that people have about nuclear energy: the risk of nuclear proliferation.
The issue is that there are materials that are used in civil nuclear power plants that potentially can be used for weapons, for nuclear weapons. The fuel that is used in nuclear power plants is very low enrichment. I mentioned 5%. That material is not weapons material.
As we mentioned earlier, we need to enrich some of the uranium to use it in power plants. In fact, we need to enrich 5% of it. To create a bomb, you would need to enrich way more uranium, at least 90% of it. There's also an issue that the uranium could be modified into plutonium, another material that could be used for weapons.
And the way to handle it, quite frankly, is to just have a very, very tight control of all those materials throughout the overall cycle. But it is a real concern, and it's something that has to be that security regime has to be strengthened as much as possible if nuclear is to grow internationally.
And then there's the third main concern: accidents. When uranium atoms are split inside of a nuclear reactor, they give off radioactive particles, which in high doses can cause terrible damage to our bodies. Now, in normal conditions, that radiation stays safely inside of the reactor. In fact, reactors are so well designed for this that a nuclear power plant actually emits less radiation than a coal-fired power plant.
The main concern that I think people have is associated with fairly spectacular, rare events, accidents.
The Chernobyl accident in 1986 in modern-day Ukraine was by far the worst.
If you look at exactly what happened at Chernobyl, the operators deliberately disabled the safety systems because they wanted to conduct an experiment. Well, you don't conduct an experiment on a commercial nuclear power plant.
As a result, the power plant exploded, releasing the radiation that was inside the reactor.
The first responders, these were soldiers of the Soviet army that were sent to basically throw sand and other materials on the burning rubble. Those were exposed to some pretty horrendous levels of radiation, and many of those died.
People who lived nearby were also exposed to radiation. The landmark report that assessed the impacts of Chernobyl found that locals who drank contaminated milk right after the accident had higher cases of cancer. And yet the same report found that the radiation that by far most people in the area experienced over their lifetime due to the accident was actually really low, well below the levels that are known to increase your risks of getting cancer. The radiation exposure was even lower for the tragic Fukushima accident, which took place in Japan in 2011.
The accident occurred following the earthquake and tsunamis, which devastated that area,
including flooding the power station, which led to the reactor leaking radiation. By the Japanese government's official count, over 2,000 people died as a result of that disaster, but not from the radiation.
For Fukushima, you're looking at a integrated over a lifetime exposure of the order of 20 millisievert. Now, what does 20 millisievert mean? So just to put things in perspective, when you go to do a CT scan to your torso or you do some kind of radiation imaging, you typically get about a third to half of that dose. And so, assuming that you do a couple of CT scans over the course of your lifetime, it's about the same amount of radiation. The evacuation of 150,000 people from the Fukushima area was a tragic mistake. The amount of damage that has been done by moving people, for example, older people out of hospitals and hospices and things of that type was much, much greater than any health damage that would have been caused by exposure of radiation because the radiation levels were so low.
Right, those 2,000 people who died from the accident, most of them were seniors or patients in hospitals who passed away due to complications of evacuating the area, not from the radiation.
It's really terrible. It's unfortunate, all to avoid 2 CT scans to the chest.
The question we're really trying to get at, of course, is nuclear power safe?
When it comes to risk and public health impact, there is no way to be particularly cheerful or positive. You have to look at the hard, cold numbers and compare. And so if you compare nuclear to coal, to natural gas, to solar, wind, hydro, other ways to generate electricity, it turns out that nuclear has the lowest, actually, mortality rate per unit energy generated.
So how can this be? Well, the World Health Organization estimates that over 3 million people worldwide die every year from asthma, lung cancer, and other illnesses caused by air pollution from fossil fuels. And I was shocked to learn that if you include worker accidents in the mix too, nuclear power has actually had a lower death toll even than solar and wind. This was really surprising for me, and it might be for you too. We're including the studies in our show notes so you can read up on it for yourself. Given all of this, the fact that nuclear power doesn't emit CO2, that it can deliver electricity on demand, that the health risks are relatively really low, and that the technology is evolving to be safer and cleaner, many energy experts think that we need to build more nuclear as part of a clean energy future.
The intermittency that is inherent in solar and wind forces you to have backup. You're going to need to meet demand, right? And if it's not met by low carbon sources like nuclear or wind, then it's met by either coal or natural gas. This is not to say that we don't need solar and wind. We do need them, and in many cases it makes perfect sense, but not alone. I think you do need a diverse portfolio. That's what all our analysis is showing, is that the best way to decarbonize is with a portfolio of low carbon technologies.
If you're hearing a running theme in this energy and climate series, it's that each clean energy technology has its benefits and its challenges, and that we can take advantage of the benefits and reduce the challenges by building a mix of different technologies. It's up to us to decide what role nuclear power plays in this mix. If you want to learn more about nuclear power, we highly recommend Dr. Buongiorno's online course from edX, which we'll link to in our show notes. He also gives a great recap of the MIT Energy Initiative's report on the future of nuclear, which you can find at energy.mit.edu/podcast. Okay, so we've talked a lot about technologies that we can deploy immediately to clean our electricity grid. But what about new, potentially big impact technologies that are on the horizon? In our next 2 episodes, we are going to dig into carbon capture and storage and fusion energy. So stick with us. Thanks to Dr. Jacopo Buongiorno for joining us today, and thank you for listening.